Ciao a tutti, and welcome to this new episode of TensorFlow Insights. In this new episode, we'll see what's TensorFlow Lite and how to use its powerful converter with the Python API. I'm Vittorio, and welcome to SVN channel. TensorFlow Lite is an open-source deep learning framework for on-device inference, like on Raspberry Pi, iOS, Android, and it comes with the TensorFlow 2 ecosystem. It provides several tools to help you deploy your model on edge devices, with three main objectives: to reduce the model size, to reduce the amount of computations, to improve latency and energy usage, and finally to adapt your model to device-specific constraints. And that's the full pipeline. You start training your model using the Keras or the low-level API. Then, after saving your model in one of these three formats, you can use the TF-Lite converter to optimize and convert your model to a much lighter format based on flat buffers. And the flat buffers is an efficient cross-platform serialization library designed to be loaded straight to RAM without any preprocessing. Finally, you can use the TF-Lite interpreter to make predictions on mobile and edge devices. But let's start with the converter. I made this notebook that, as always, you can find in the description below, with all the possible conversions that you can perform with the TF-Lite converter. Okay, let's start importing some libraries, setting some paths, and then train a very simple convolutional neural network on the MNIST dataset that will be our reference model to convert with the TF-Lite converter. Let's import the dataset and transform it in a tf.data.dataset. Then define a model with the sequential API, very simple convolutional neural network, compile it and train it, and this will take a while. Train finished, we can evaluate it. 0.99, not bad I think, and save it with the saved model and Keras format. Now we can start with the first TF-Lite conversion. A simple TF-Lite conversion prunes all operations that are not needed to make predictions, such as training operations, and optimizes computations whenever it's possible. First of all, we can create a converter importing a model saved in one of the three available formats. In our case, we can use this one. Once the converter is instantiated, we can call the convert method to convert the model and receive as output the actual converted model and save it. Let's further optimize our graph. Quantization. Quantization is simply convert weights and activations to a lower precision, for example, float 16. The pipeline is very similar. Load the model, then, and this is the only difference, I already ran it, give some instructions to the converter, in this case this one, and then the target quantization. Then call the convert method and again save it. That's it. What about going deeper with quantization? There are three ways to quantize our model to 8-bit quantization: dynamic range quantization, integer quantization with float fallback, and full integer quantization. With the first one, dynamic range quantization, only weights are quantized, but at inference are dequantized back to float 32. As always, let's load the model, give some instructions to the converter and convert it, and finally save it. Instead, integer quantization with float fallback quantizes everything, weights and activations. But if it finds an operation that is not supported, it falls back to float 32. Moreover, for compatibility reasons, input and output are still in float 32. To have everything in int 8, we need to do full integer quantization. For both these two conversions, we need a representative dataset. So we needed to create a generator with our training set pre-processed in the same way of the training, and then set the number of calibration steps in order to say to the converter how many images to use during the conversion. So we can load the model, pass the generator, convert it, and save it. Finally, for the full integer quantization, we simply needed to specify a little bit more options, convert it, and save it. That's it. Okay, thank you for watching. Don't forget to subscribe for more videos, and see you for the next episode of TensorFlow Insights.